In the vast darkness of space, more than 14 billion miles from Earth, two human-made objects continue their lonely journey into the cosmic unknown. The Voyager spacecraft represent humanity's most distant physical emissaries, carrying our technological achievements and cultural heritage beyond the boundaries of our solar system. Launched in 1977 during the height of the space race, these twin explorers were initially designed for a 5-year mission to study Jupiter and Saturn. Yet, more than 4 decades later, they continue to function, having completed an unprecedented grand tour of the outer planets before crossing the threshold into interstellar space. The Voyager mission stands as one of humanity's greatest exploratory achievements, a testament to scientific curiosity, engineering brilliance, and our innate desire to push beyond known frontiers. This is the story of Voyager, made at the edge of the solar system, but destined for the stars. In the cold vacuum of space, over 14 billion miles from Earth, a human-made object continues its journey into the cosmic unknown. The Voyager spacecraft represent humanity's most distant physical emissaries, carrying our technological achievements and cultural heritage beyond the boundaries of our solar system. Their story begins not at the edge of interstellar space where they now travel, but in the politically charged atmosphere of 1960s America, amid a combination of scientific curiosity, Cold War competition, and technological innovation. The genesis of the Grand Tour. The conceptual origins of what would become the Voyager mission can be traced to the late 1960s, when astronomers and mission planners at NASA recognized a rare astronomical alignment that would occur in the late 1970s and early 1980s. This alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, occurs roughly once every 176 years. It presented a unique opportunity for a spacecraft to visit multiple outer planets on a single mission, using a technique called gravity assist to slingshot from one planet to the next. Gary Flandreau, a young engineer at NASA's Jet Propulsion Laboratory, JPL, made this crucial discovery in 1965 while analyzing potential trajectories for future planetary missions. His calculations revealed that a spacecraft launched in the late 1970s could take advantage of the gravitational fields of each planet it encountered to accelerate toward the next destination, dramatically reducing the fuel requirements and travel time between planets. This trajectory became known as the Grand Tour. The political context of the era cannot be overlooked in understanding how the Voyager program came to fruition. The United States and Soviet Union were locked in the space race, a technological competition that represented one facet of the broader Cold War. Following the remarkable success of the Apollo moon landings, NASA was seeking new frontiers to explore. The Grand Tour concept offered a compelling next step in planetary exploration that would demonstrate American technological prowess. Initially, NASA envisioned an ambitious Grand Tour program with multiple spacecraft launched between 1976 and 1979, visiting all the outer planets. However, budget constraints in the early 1970s forced NASA to scale back these plans. The cancellation of Apollo missions 18, 19, and 20 signaled a new era of fiscal restraint in American space exploration. The original Grand Tour was considered too expensive and was replaced by a more modest proposal: the Mariner Jupiter-Saturn 1977 mission, which would eventually evolve into the Voyager program. Engineering challenges and innovations. Creating spacecraft capable of surviving the harsh conditions of deep space for years, potentially decades, presented unprecedented engineering challenges. The Voyager spacecraft had to endure extreme temperature variations, cosmic radiation, and micrometeoroid impacts while maintaining communication with Earth across ever-increasing distances. The physical design of each Voyager spacecraft is a marvel of 1970s engineering. Standing 13 feet tall and weighing approximately 1,820 pounds, 825 kilograms, each spacecraft carries a suite of scientific instruments mounted on a 10-sided main bus. The most visually distinctive feature is the 12-foot, 3.7-meter diameter high-gain antenna, which maintains communication with Earth. Extending outward from the bus are booms carrying the magnetometers and other instruments that needed to be isolated from the electromagnetic interference of the main spacecraft. Power generation presented a particular challenge for a mission expected to operate far from the sun, where solar panels would be ineffective. The solution came in the form of radioisotope thermoelectric generators, RTGs, which convert heat from the natural decay of plutonium-238 into electricity. Each Voyager carries 3 RTGs that initially provided about 470 watts of power at launch. This power output gradually decreases over time as the plutonium decays, necessitating careful power management strategies that continue to this day. The computing capacity of the Voyager spacecraft seems remarkably limited by modern standards. Each spacecraft contains 3 interconnected computer systems, one for attitude control and navigation, one for command processing and sequencing, and one for data collection and transmission. The spacecraft's computer memory consists of just 69 kilobytes, less than the size of a typical digital photograph today. Yet, these modest computing resources have proven sufficient for nearly half a century of operation. Communication across vast interplanetary distances required innovative solutions. The spacecraft transmit data to Earth via radio waves at a power of just 23 watts, comparable to a refrigerator light bulb. Yet this faint signal, captured by NASA's Deep Space network of radio antennas, has allowed scientists to receive billions of bits of scientific data. The data transmission rate has decreased as the distance increases, from 115,200 bits per second during the Jupiter and Saturn encounters to mere 160 bits per second today. The scientific payload aboard each Voyager spacecraft includes instruments designed to study magnetic fields, cosmic rays, plasma waves, and planetary atmospheres. The identical spacecraft carry Imaging Science System, ISS, a dual-camera system providing visible light, photographs, Radio Science System, RSS, using the spacecraft's radio transmitter to study atmospheric composition and density, infrared interferometer spectrometer, IRIS, measuring infrared radiation to study thermal properties, ultraviolet spectrometer, UVS, measuring ultraviolet emissions from atmospheric gases, magnetometer, MAG, measuring magnetic fields, plasma science, PLS, studying the solar wind and planetary magnetospheres, low energy charge particle, LECP, detecting low energy particles in planetary, magnetospheres, cosmic ray system, CRS, measuring high energy charge particles, planetary radios astronomy, PRA, detecting radio emissions from the planets, photopolarimeter system, PPS, measuring polarization of light to study surface texture and atmospheric composition, plasma wave system, PWS, detecting plasma waves in planetary magnetospheres. Perhaps the most culturally significant payload item is the Golden Record, a 12-inch gold-plated copper disc containing sounds and images representing Earth and humanity. Curated by a committee chaired by astronomer Carl Sagan, this time capsule was designed to communicate information about Earth to any extraterrestrial intelligence that might recover the spacecraft in the distant future. The record contains 115 images, natural sounds of Earth, musical selections from different cultures, and greetings in 55 languages. The cover of the record includes symbolic instructions for playing it and a map showing Earth's location in the galaxy. The launch campaign, the summer of 1977, marked the culmination of years of planning, design, and construction. The twin Voyager spacecraft were prepared for launch at Kennedy Space Center in Florida amid the humid summer heat. Interestingly, although Voyager 2 was launched first on August 20th, 1977, Voyager 1 was named first because it would reach Jupiter and Saturn sooner due to its faster trajectory. Voyager 2 lifted off aboard a Titan IIIe Centaur rocket at 10:29 a.m. Eastern Time. 16 days later, on September 5, 1977, Voyager 1 followed on an identical launch vehicle at 8:56 a.m. Both launches were successful, placing the spacecraft on their respective trajectories toward Jupiter. While the two spacecraft initially carried the designation Mariner Jupiter-Saturn, they were officially renamed Voyager shortly after launch. The launch sequence for each mission was complex and precisely choreographed. After the initial boost from the Titan first and second stages, the Centaur upper stage ignited to place the spacecraft on a parking orbit around Earth. A second Centaur burn then propelled the spacecraft out of Earth orbit and onto a trajectory toward Jupiter. Following separation from the Centaur stage, the spacecraft deployed their booms and antennas and established communication with Earth. An interesting quirk of interplanetary physics meant that the later launched Voyager 1 would overtake Voyager 2. This occurred because Voyager 1 was intentionally placed on a faster trajectory that would take it to Jupiter first. The trade-off for this speed was that after encountering Saturn, Voyager 1 would be directed northward out of the ecliptic plane, the flat plane in which most planets orbit the Sun, ending its planetary tour. Voyager 2, moving more slowly, would continue on to Uranus and Neptune, completing a more comprehensive grand tour. Early mission operations and course corrections. The first few months of the mission were dedicated to checkout operations and trajectory refinements. Several course correction maneuvers were performed to ensure the spacecraft would arrive at their Jupiter encounter points with the necessary precision. These maneuvers were critical, as even small errors in trajectory would be magnified over the vast distances to the outer planets. Mission controllers faced an early crisis when Voyager 2's primary radio receiver failed just 3 months into the mission. Fortunately, the spacecraft carried a backup receiver that was activated and has functioned for the remainder of the mission. This early equipment failure highlighted the importance of redundant systems for deep space missions. By December 1977, both spacecraft had passed the orbit of Mars, still less than a year into what would become a multi-decade journey. The primary mission objectives were clearly defined: conduct close-up studies of Jupiter and Saturn, their satellites, and Saturn's rings, and if feasible, continue on to explore Uranus and Neptune. The spacecraft were also tasked with studying the interplanetary medium, the sparse matter and radiation that exist between planets. As the twin Voyagers sailed into the asteroid belt, that region of space between Mars and Jupiter populated with countless rocky bodies, mission scientists held their breath. Unlike their predecessors, the Pioneer 10 and 11 spacecraft, the Voyagers had not been specifically designed to withstand micrometeoroid impacts. The successful passage through this potential hazard zone marked another milestone in the early mission. The scientific context. The Voyager mission represented a significant advancement in our approach to planetary exploration. Prior to Voyager, knowledge of the outer planets came primarily from Earth-based observations and the earlier Pioneer 10 and 11 missions, which had conducted flyby reconnaissance of Jupiter and Saturn in the early 1970s. While groundbreaking, these Pioneer missions carried more limited scientific instrumentation than the Voyagers and returned fewer images. The scientific community harbored many questions about the outer planets that Voyager was designed to address. What powered Jupiter's Great Red Spot? What was the composition of Saturn's rings? Did Titan, Saturn's largest moon, have a substantial atmosphere that might harbor organic compounds? These and countless other questions awaited answers that only close-up observation could provide. In many ways, the Voyager mission represented a transition in NASA's approach to planetary exploration. The reconnaissance phase of the 1960s and early 1970s was giving way to more comprehensive exploration. Voyager's instrument suite was designed to provide a holistic view of each planetary system it encountered, studying not just the planets themselves, but their moons, rings, magnetic fields, and surrounding space environment. As the spacecraft journeyed through the inner solar system in late 1977 and 1978, scientists and engineers continued to refine the encounter sequences that would be used at Jupiter. The increasing distance from Earth meant that communication delays were growing longer, necessitating more autonomous operation by the spacecraft. By the time the spacecraft reached Jupiter, radio signals would take approximately 45 minutes to make the round trip between Earth and the spacecraft. The successful launches and early operations of the Voyager spacecraft represented the beginning of what would become one of humanity's greatest exploratory endeavors. Little did the mission planners know that these remarkable machines would still be operating and returning scientific data more than 4 decades later, having traversed the entire solar system and ventured into interstellar space. The Voyager mission had begun its grand tour, carrying humanity's message to the stars and forever changing our understanding of our cosmic neighborhood. The Grand Tour. Planetary Encounters. The Voyager spacecraft's journey through our solar system represents one of humanity's greatest exploratory achievements, a celestial grand tour that revolutionized our understanding of the outer planets and their complex systems. As these twin ambassadors of Earth ventured into previously unexplored territory, they unveiled cosmic wonders that reshaped planetary science and ignited the imagination of the world. Jupiter, the first giant. The planetary phase of the Voyager mission began in earnest when Voyager 1 approached the Jupiter system in January 1979, with its closest approach occurring on March 5, 1979, at a distance of about 217,000 miles, 349,000 kilometers from the planet's center. Voyager 2 followed, making its closest approach on July 9, 1979. Jupiter, the solar system's largest planet, presented an awe-inspiring sight through Voyager's cameras. The spacecraft revealed the gas giant's atmosphere in unprecedented detail, showing it to be a turbulent, dynamic environment dominated by complex weather patterns. The Great Red Spot, a storm that had been observed from Earth for centuries, was revealed to be a massive anticyclonic storm, large enough to engulf several Earths. The Voyagers documented its counterclockwise rotation, completing one revolution every 6 days. Beyond simply photographing Jupiter's colorful bands and zones, Voyager's instruments analyzed their composition and structure. The spacecraft detected lightning and aurora in Jupiter's atmosphere, phenomena previously unknown on other planets. Jupiter's powerful magnetic field, the strongest in the solar system, was mapped in detail, revealing a magnetosphere that extends millions of miles into space and traps dangerous radiation belts in the system, the existence of which had been suspected but not confirmed. By the time the Jupiter encounters were complete, our understanding of the Jovian system had been fundamentally transformed. Saturn, Lord of the Rings. After their encounters with Jupiter, both spacecraft used the planet's gravitational field to slingshot towards Saturn. Voyager 1 reached the Saturn system in November 1980, with its closest approach on November 12th, while Voyager 2 arrived in August 1981. Saturn's most distinctive feature, its magnificent ring system, was the primary focus of the Voyager's investigations. Prior to the mission, scientists knew of 3 main rings, designated A, B, and C. The Voyagers revealed that Saturn's rings are actually composed of thousands of narrow ringlets, like the grooves on a phonograph record. These intricate structures suggested complex gravitational interactions between the rings and Saturn's many moons. The spacecraft discovered previously unknown phenomena in the rings, including spoke-like features that rotate with the rings, suggesting the influence of Saturn's magnetic field on dust particles. They observed waves and gaps in the rings, many caused by gravitational resonances with nearby moons. The F ring, barely visible from Earth, was found to be twisted and braided in places, shepherded by 2 small moons, Prometheus and Pandora, discovered during the encounters. Saturn itself, while similar to Jupiter in its composition of primarily hydrogen and helium, displayed less dramatic atmospheric features. Its banded structure was more subdued, partially obscured by a high-altitude haze. However, the Voyagers detected a hexagonal cloud pattern around Saturn's north pole, a geometric oddity that remains not fully explained to this day. Saturn's family of moons proved to be diverse and fascinating. Titan, the largest, was of particular interest due to its substantial atmosphere, the only moon in our solar system with a thick atmosphere. Voyager 1's trajectory was specifically designed to provide a close flyby of Titan, approaching within 4,000 miles, 6,500 kilometers, of its surface. While the cameras could not penetrate Titan's orange haze to view the surface, other instruments analyzed its atmosphere, determining it to be primarily nitrogen with traces of methane and other hydrocarbons. This chemistry suggested the possibility of organic compounds forming in conditions that might resemble Earth's primordial environment. Other Saturnian moons displayed remarkable diversity. Mimas, with its enormous Herschel crater, which gives it a resemblance to the fictional Death Star, appeared to have barely survived a catastrophic impact. Enceladus showed surprisingly smooth regions, hinting at recent geological activity that would be confirmed by later missions. Hyperion revealed an unusual sponge-like appearance and chaotic rotation. In total, the Voyagers discovered several new moons: Atlas, Prometheus, Pandora, and others. Following the Saturn encounter, Voyager 1's primary mission was complete. Its trajectory took it northward out of the ecliptic plane, away from the planets and toward interstellar space. Voyager 2, however, continued on a trajectory that would enable it to visit the two outermost giant planets, Uranus, the sideways world. On January 24, 1986, Voyager 2 made its closest approach to Uranus, coming within 50,600 miles, 81,500 kilometers, of the planet's cloud tops. This encounter represented the first, and to date only, close-up study of the seventh planet from the Sun. Uranus presented a remarkably featureless appearance. Unlike Jupiter and Saturn with their colorful bands, Uranus appeared as a nearly uniform blue-green sphere. This blandness was attributed to a high-altitude methane haze that obscured deeper atmospheric features. Nevertheless, by processing images to enhance contrast, scientists were able to detect some cloud structures and measure wind speeds in the Uranian atmosphere. The most striking characteristic of Uranus is its extreme axial tilt of 98 degrees, which causes it to rotate on its side relative to its orbital plane. This unusual orientation, likely the result of a catastrophic collision in the solar system's early history, means that Uranus experiences extreme seasonal variations, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Uranus's magnetic field provided another surprise. Unlike the magnetic fields of other planets, which are roughly aligned with their rotational axes, Uranus's magnetic field is tilted 59 degrees from its rotational axis and offset from the planet's center. This unusual configuration created a corkscrew-shaped magnetosphere as the planet rotated. The Voyager 2 encounter revealed 10 previously unknown moons orbiting Uranus, bringing the total known at that time to 15. The larger moons, Miranda, Ariel, Umbriel, Titania, and Oberon, were imaged in detail, revealing varied geological features. Miranda, in particular, surprised scientists with its bizarre patchwork appearance, suggesting a violent history possibly including the breakup and reassembly of the moon early in its history. Uranus was also found to possess a system of rings, though much darker and less spectacular than Saturn's. 11 distinct rings were identified, composed of dark particles ranging from dust-sized to boulder-sized. Neptune, the final planet. Voyager 2's last planetary encounter occurred on August 25, 1989, when it flew within 3,000 miles, 4,800 kilometers, of Neptune's North Pole. Despite being the most distant planet visited, the Neptune encounter was in many ways the most dramatic. Contrary to expectations, Neptune's atmosphere proved to be remarkably active, with visible storm systems and the fastest winds measured in the solar system, up to 1,500 miles, 2,400 kilometers per hour. The most prominent feature was the Great Dark Spot, a storm system comparable in size to Earth, accompanied by bright, high-altitude clouds nicknamed scooters that zipped around the planet. Like Uranus, Neptune possesses a magnetic field significantly tilted from its rotational axis, though the offset from the planet's center is much greater, suggesting complex dynamo processes in the planet's interior. Subsequently, Neptune's moon system provided another highlight of the encounter. While 6 new moons were discovered, it was Triton that captivated scientists' attention. Slightly smaller than Earth's moon, Triton orbits Neptune in a retrograde direction, opposite to the planet's rotation, suggesting it was captured rather than formed alongside Neptune. Voyager 2 revealed Triton to be geologically active, with nitrogen geysers erupting from its southern polar cap. With a surface temperature of -391 degrees Fahrenheit, -235 degrees Celsius, Triton is one of the coldest objects in the solar system. The spacecraft also observed Neptune's ring system, which consists of several faint rings with curious clumpy structures dubbed ring arcs that defied explanation until later theoretical work. The Golden Record, a message to the stars. Throughout their grand tour, the Voyager spacecraft carried a special payload, the Golden Records. These 12-inch gold-plated copper discs contain sounds and images representing the diversity of life and culture on Earth. Selected by a committee chaired by astronomer Carl Sagan, the records include 115 images, greetings in 55 languages, a variety of natural sounds, and musical selections from different cultures and eras. In Nisr, the Golden Records were designed to last for billions of years in the interstellar medium. They represent humanity's message to the cosmos, a time capsule of Earth circa 1977. Each record is encased in an aluminum jacket with a cover diagram that provides instructions for playing the record and a pulsar map indicating Earth's location. ISI. While the probability of the records ever being found by extraterrestrial intelligence is vanishingly small, they serve an important symbolic purpose. As Sagan noted, the spacecraft will be encountered, and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Scientific legacy of the Grand Tour. The Voyager encounters with the outer planets fundamentally transformed our understanding of the solar system. Prior to these missions, the gas giants were little more than blurry disks in even the most powerful telescopes. After Voyager, they emerged as complex worlds with active atmospheres, unique magnetic fields, and diverse families of moons, many of which could be considered planets in their own right. The mission's discoveries continue to influence planetary science and exploration. The evidence of a subsurface ocean on Europa led directly to NASA's Europa Clipper mission, scheduled to launch in the 2020 S. The mysterious nitrogen geysers on Triton have made Neptune's moon a target of interest for future missions. The complex chemistry of Titan's atmosphere inspired the Cassini-Huygens mission and the upcoming Dragonfly mission. Perhaps most importantly, the Voyager Grand Tour demonstrated the value of comparative planetology, studying similar processes across different worlds to better understand fundamental principles. By observing how magnetic fields, atmospheres, and geological processes manifest under different conditions, scientists gained insights impossible to obtain from studying Earth alone. Sapinal. As the Voyager spacecraft left Neptune behind in 1989, they had completed the most extensive planetary reconnaissance mission in history, forever changing our perspective on our solar system and our place within it. But their journey was far from over. The most distant phase of their mission, the exploration of interstellar space, was just beginning. Entering interstellar space. As the twin Voyager spacecraft completed their grand tour of the outer planets, they embarked upon a new and unprecedented phase of their mission, the exploration of interstellar space. This transition from planetary explorer to interstellar probe represented not only a remarkable scientific achievement, but also a profound symbolic milestone for humanity. For the first time, objects created by human hands would venture beyond the protective bubble of our sun's influence and into the vast cosmic ocean that exists between star systems, the Heliosphere, our sun's domain. To understand the significance of the Voyager's journey into interstellar space, we must first understand the structure of the Heliosphere, the region dominated by the sun's influence. The heliosphere is created by the solar wind, a continuous stream of charged particles flowing outward from the sun in all directions at speeds of about 1 million miles per hour. This solar wind creates a bubble-like region in space where the sun's magnetic field and particle emissions dominate over the interstellar medium. Tsawar, the heliosphere has several distinct regions and boundaries. At its inner edge lies the termination shock, where the supersonic solar wind abruptly slows as it begins to feel the pressure of the interstellar medium. Beyond this lies the heliosheath, a turbulent region where the slowed solar wind is compressed and turbulent. The outer boundary of the heliosphere is called the Heliopause, the place where the pressure of the solar wind balances the pressure of the interstellar medium. Beyond the heliopause lies interstellar space, dominated by material from other stars and the accumulated debris of countless stellar explosions throughout our galaxy's history. Before the Voyager mission, the structure and extent of the heliosphere remained largely theoretical. While scientists had developed models based on limited data, no spacecraft had traveled far enough to directly sample the outer regions of the heliosphere or to cross its boundaries. The Voyagers provided the first opportunity to test these models against direct observations. The Voyager interstellar mission. After Voyager 2 completed its encounter with Neptune in August 1989, NASA formally initiated the Voyager interstellar mission, VIM. This extended mission had three primary scientific objectives: to investigate the interplanetary medium, to characterize the interaction between the solar wind and the interstellar medium, and to search for the heliopause boundary. To conserve power and extend the operational lifetime of the spacecraft, mission controllers began powering down non-essential instruments. By the early 1990s, the cameras that had captured the iconic images of the outer planets had been deactivated, as they would serve no further purpose in the darkness beyond Neptune. The focus shifted to the instruments that could directly measure the particles and fields in the spacecraft's environment: the magnetometer, plasma wave subsystem, cosmic ray subsystem, and low-energy charged particle instrument. As the Voyagers continued their outward journey at speeds of roughly 35,000 miles per hour, 56,000 kilometers per hour, scientists waited patiently for signs of approaching the heliosphere's edge. The first significant milestone came in 2004 when Voyager 1, then about 94 astronomical units from the Sun, 1 astronomical unit equals the average Earth-Sun distance of 93 million miles, detected a strong shock wave in the solar wind, the termination shock. This detection confirmed theoretical predictions about the heliosphere's structure and provided the first direct evidence that the spacecraft was approaching interstellar space. Voyager 2, following a different trajectory and moving slightly slower, crossed the termination shock in 2007 at a distance of 84 astronomical units from the Sun. The difference in these crossing distances revealed that the heliosphere is not perfectly spherical, but is compressed in the direction of the Sun's motion through the galaxy. The heliosheath, a turbulent borderland. After crossing the termination shock, both spacecraft entered the heliosheath, a region unlike any previously explored. In this turbulent borderland between solar and interstellar influence, the Voyagers detected complex structures in the magnetic field and unusual patterns in charged particle distributions. The heliosheath proved to be a region of surprises. Scientists had expected the solar wind in this region to be deflected sideways as it approached the heliopause, creating a flow pattern parallel to the boundary. Instead, Voyager 1 found that the solar wind effectively came to a complete stop, with no detectable outward motion. This stagnation region had not been predicted by existing models and suggested that the interaction between the solar and interstellar environments was more complex than previously thought. Another unexpected finding in the heliosheath was the discovery of a magnetic highway, or magnetic freeway. In this region, detected by Voyager 1 in 2012, the magnetic field lines connected the Sun's magnetic field to the interstellar magnetic field, allowing easier passage of certain charged particles. Lower energy particles from inside the heliosphere could escape, while higher energy cosmic rays from interstellar space could enter more easily. This phenomenon provided an important clue that the spacecraft was approaching the heliopause. Throughout their journey through the heliosheath, both Voyagers continued to detect energetic particles generated by eruptions on the Sun, confirming they remained within the Sun's magnetized bubble. However, the intensity of cosmic rays from outside the solar system steadily increased, another sign that the boundary to interstellar space was approaching. Crossing the heliopause, Voyager 1. On August 25, 2012, Voyager 1 experienced a dramatic change in its environment. The spacecraft detected a sudden increase in the density of electrons around it, accompanied by an abrupt decrease in particles originating from within the heliosphere. Simultaneously, the magnetic field strength increased significantly, but maintained the same direction. These changes suggested that Voyager 1 had crossed a significant boundary, but scientists remained cautious about declaring that the spacecraft had entered interstellar space. After careful analysis of the data over the following months, NASA announced on September 12, 2013, that Voyager 1 had indeed crossed the Heliopause and entered interstellar space on August 25, 2012. At the time of crossing, the spacecraft was approximately 121 astronomical units, 11.25 billion miles, or 18.1 billion kilometers, from the Sun, making it the first human-made object to enter the realm between stars. The confirmation came from a fortuitous solar eruption in March 2012, when the plasma from this eruption reached Voyager 1 in April 2013. It caused the plasma around the spacecraft to oscillate. By measuring the frequency of these oscillations, scientists could determine the plasma density. The density was found to be about 80 times higher than typically found inside the heliosphere, consistent with theoretical predictions for interstellar space. "Now we're in a truly alien environment," said Ed Stone, Voyager project scientist. "We're in a place that nothing from Earth has been before." This historic milestone represented not only a triumph of engineering and scientific persistence, but also a symbolic moment for humanity. Our first physical emissary had left the protective bubble of our star and entered the vast space between stars, crossing the Heliopause, Voyager 2. Voyager 2 followed its twin into interstellar space on November 5, 2018, at a distance of 119 astronomical units, 11.1 billion miles, or 17.8 billion kilometers, from the Sun. Unlike Voyager 1, Voyager 2 had a functioning plasma science instrument that could directly measure the properties of the surrounding plasma, providing more definitive data about the transition. The crossing was marked by a steep decline in solar particles and a corresponding increase in galactic cosmic rays. The plasma science instrument detected a 100-fold decrease in solar wind particles and a significant increase in plasma density, confirming the spacecraft had entered the interstellar medium. Interestingly, Voyager 2 crossed the Heliopause at a slightly different distance from the Sun than Voyager 1, further confirming that the heliosphere is asymmetrical. This asymmetry is likely caused by the interstellar magnetic field pressing inward on the southern hemisphere of the heliosphere. The Voyager 2 crossing provided a valuable second data point, allowing scientists to compare measurements from two different locations and times. These comparisons revealed that the Heliopause appears to be a somewhat fluid boundary that may expand and contract with changes in solar activity rather than a fixed border. Characteristics of interstellar space. The Voyager's measurements have begun to paint a picture of interstellar space that both confirms some. Launched in 1977, each Voyager's RTGs produced about 470 watts of electrical power. By 2023, this had decreased to less than 250 watts, requiring careful management of the spacecraft's systems. Engineers regularly power down components to ensure that the most critical systems can continue to function. The extreme cold of interstellar space, with temperatures approaching absolute zero, presents thermal challenges. Some components must be kept warm using strategically placed heaters, which further taxes the limited power supply. Despite these challenges, both spacecraft have demonstrated remarkable durability, with primary systems continuing to function more than 4 decades after launch. Data transmission rates have decreased dramatically as the distance increases. The spacecraft now transmit at a mere 160 bits per second, compared to the 115,200 bits per second during the planetary encounters. This limits the amount of scientific data that can be downloaded in a given communication session, requiring careful prioritization of data collection. The Deep Space Network, NASA's system of large radio antennas located in California, Spain, and Australia, must dedicate its most sensitive receivers to detect the incredibly faint radio signals from the Voyagers. These signals, by the time they reach Earth, have a power of less than a femtowatt, 10 circumflex 15 watts, billions of times weaker than the power of a typical digital watch. The meaning of Voyager in interstellar space. The presence of human-made objects in interstellar space carries profound philosophical and cultural significance beyond the scientific data returned. The Voyagers represent humanity's first tentative physical reach beyond our solar system, tangible emissaries carrying evidence of our civilization into the cosmic void. Carl Sagan, who championed the Golden Record project, captured this significance eloquently. The spacecraft will be encountered, and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The Voyagers have transformed our conception of our place in the cosmos. They have mapped the true extent of our sun's influence and provided the first direct measurements of the environment that exists between stars. In doing so, they have helped us understand Earth's place within the protective bubble of the Heliosphere and the nature of the vast spaces that separate star systems. As the Voyagers continue their journey into the Milky Way, they remind us of the remarkable achievement they represent, a testament to human curiosity, engineering prowess, and collective scientific endeavor. Though they will eventually fall silent as their power sources fail, they will continue their silent passage through the galaxy for billions of years, perhaps outlasting Earth itself, as testament to a civilization that dared to reach for the stars. In the words of Jimmy Carter, whose message is carried on the Golden Record, "This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." Technical challenges and innovations. The Voyager spacecraft represent a pinnacle of engineering achievement, machines designed in the technological environment of the 1970s that continue to function and return scientific data more than 4 decades later while operating in the harshest imaginable conditions. The technical challenges overcome during the design, construction, and operation of these spacecraft were formidable, and the innovations developed to address them have influenced spacecraft design ever since. From power generation to data storage, communications to navigation, every system aboard the Voyagers required creative solutions to unprecedented problems. Designing for the unknown. When engineers at the Jet Propulsion Laboratory, JPL, began designing the Voyager spacecraft in the early 1970s, they faced a fundamental challenge: creating machines that could survive and function in environments never before encountered by human-made objects. The outer solar system remained largely mysterious, with limited data available about the conditions the spacecraft would face. The spacecraft would need to endure extreme temperature variations, from the relative warmth near Earth to the cold of deep space. They would have to withstand intense radiation, particularly during the Jupiter flyby, where the radiation environment was suspected, and later confirmed, to be extraordinarily harsh. They would need to operate autonomously for long periods, as the increasing communication delay would make real-time control from Earth impossible. And they would need to do all this while maintaining precise pointing for both scientific observations and Earth communications. The engineering team adopted a philosophy of redundancy and robustness. Critical systems were duplicated, with backup components that could be activated if primary systems failed. Where possible, systems were designed with broad operating parameters to function under a wide range of conditions. This approach proved prescient. When Voyager 2's primary radio receiver failed early in the mission, the backup system took over seamlessly and has operated ever since. Another design philosophy was modularity. The spacecraft were constructed from interchangeable components where possible, simplifying construction and testing. This approach also allowed engineers to address problems discovered during testing by replacing specific modules rather than redesigning entire systems. The physical structure of each Voyager spacecraft reflects these design principles. The main body is a decagonal, 10-sided bus housing the electronics and propellant tanks. A 3.7-meter high-gain antenna is mounted on one face for communication with Earth. Extending from the bus are booms carrying scientific instruments that needed to be isolated from the electromagnetic interference of the main spacecraft. The entire structure is dominated by the distinctive shape of the high-gain antenna, and the 3 radioisotope thermoelectric generators, RTGs, mounted on a boom extending away from sensitive instruments. Power management with RTGs. Perhaps the most fundamental technical challenge for the Voyager mission was power generation. The spacecraft would operate far from the Sun, where solar panels, the power source for many near-Earth spacecraft, would be ineffective. At Jupiter's distance, solar energy is only about 4% as intense as at Earth. By Neptune, it drops to less than 0.2%. The solution came in the form of radioisotope thermoelectric generators, RTGs, devices that convert heat from the natural radioactive decay of plutonium-238 into electricity. Each Voyager carries 3 RTGs, initially providing about 470 watts of electrical power at launch. This power output gradually decreases over time as the plutonium decays, with a half-life of 87.7 years. The RTGs represented a significant engineering challenge themselves. They needed to be safe to launch, with multiple containment systems ensuring no release of radioactive material even in a launch accident, efficient in converting thermal energy to electricity, and reliable for decades of continuous operation. The thermoelectric conversion technology uses the Seebeck effect, where a temperature difference across 2 different metals or semiconductors creates an electric voltage. While simple in principle, implementing this technology for long-term space applications required careful material selection and thermal design. The declining power output of the RTGs has necessitated increasingly careful power management throughout the mission. By 2023, each spacecraft was operating with less than 250 watts of available power, roughly equivalent to a few incandescent light bulbs. This power decline has required mission controllers to develop creative power-saving strategies, sequentially turning off non-essential systems and instruments to extend the operational life of the most critical components. A particularly innovative aspect of the power system is its integration with the spacecraft's thermal management. In the vacuum of space, an object can only gain or lose heat through radiation. Without an atmosphere to provide conduction or convection, keeping components within their operating temperature ranges requires careful thermal design. The waste heat from the RTGs is directed through the spacecraft using thermal radiators and heat pipes to keep critical components warm in the cold of deep space. As power output has decreased, this has created additional thermal challenges as less waste heat is available for warming vital systems. Communications across billions of miles. Communicating with spacecraft across vast interplanetary distances presented another formidable technical challenge. The Voyagers communicate with Earth via radio waves at frequencies of 2.3 GHz S-band and 8.4 GHz X-band, transmitting data at powers as low as 23 watts, comparable to a refrigerator light bulb. By the time these signals reach Earth from interstellar space, they have a power of less than a femtowatt, 10 circumflex 15 watts, so faint that only the world's most sensitive radio telescopes can detect them. The primary element of the communication system is the high-gain antenna, a 3.7-meter parabolic dish that must be precisely pointed toward Earth to maintain communication. Early in the mission, the spacecraft could rotate to direct this antenna while performing scientific observations in other directions. As power has decreased, the spacecraft now remain in a fixed orientation with the antenna pointed toward Earth, rotating only occasionally when specific observations require it. Receiving these faint signals on Earth requires NASA's Deep Space Network, DSN, a system of massive radio antennas located at 3 sites around the globe: Goldstone, California, Madrid, Spain, and Canberra, Australia. The largest of these antennas are 70 meters in diameter, equipped with extremely sensitive receivers cooled to near absolute zero to minimize electronic noise. The DSN represents a technical marvel in its own right, capable of detecting signals billions of times weaker than those of a typical cell phone. And no, data transmission rates have decreased dramatically as the distance has increased. During the Jupiter and Saturn encounters, the spacecraft could transmit data at rates up to 115,200 bits per second. By the time of the Neptune encounter, this had decreased to 21,600 bits per second. Today, The data rate is a mere 160 bits per second, slower than the earliest computer modems of the 1960s. This limited bandwidth requires careful planning of scientific observations and data transmission schedules. To maximize the scientific return given these constraints, the mission developed sophisticated data compression techniques. Images, for example, are encoded using various compression algorithms to reduce the amount of data that must be transmitted without significantly degrading scientific value. These techniques pioneered approaches that would later influence image and data compression technologies used on Earth. Computing and data storage. The computing capabilities of the Voyager spacecraft are almost unimaginably primitive by modern standards, yet they have proven sufficient for decades of complex operations. Each spacecraft contains 3 interconnected computer systems: the Computer Command System, CCS, for basic spacecraft control, the Flight Data System, FDS, for managing science instruments, and the Attitude and Articulation Control System, AACS, for orientation and pointing. The primary computer, the CCS, has a processing speed of about 80 kHz, millions of times slower than a modern smartphone. Its memory consists of just 69 kilobytes, less than the size of a small digital image today. The software is written in machine language specific to the custom-built processors, with instructions executed sequentially from memory. Data storage was provided by a digital tape recorder, DTR, which could store up to 536 megabits, about 67 megabytes, of data on magnetic tape. This technology, similar to the cassette tapes popular in the 1970s, has long since been obsolete on Earth, but continues to function in the depths of space. The tape systems have far exceeded their design lifetime, and engineers must carefully manage their use to prevent mechanical failures. The limited computing resources required innovative approaches to spacecraft autonomy. The Voyagers were designed with fault protection systems that could detect and respond to problems without waiting for commands from Earth. These systems can place the spacecraft in safe mode during emergencies, shutting down non-essential systems and orienting the Huygens antenna toward Earth to await further instructions. The software controlling the spacecraft has been repeatedly updated throughout the mission to address new requirements and work around hardware limitations as components aged. These updates must be designed with extreme care, as errors could potentially end the mission. The process of uploading new software across billions of miles, with round-trip communication times of many hours, requires meticulous planning and validation. Navigation and trajectory control. Navigating spacecraft to precise encounters with planets billions of miles from Earth presented unprecedented challenges in orbital mechanics and trajectory control. The Voyager mission pioneered techniques for gravity assist maneuvers, using a planet's gravity to alter a spacecraft's trajectory and increase its velocity without expending propellant. The concept of gravity assists was first applied successfully by the Mariner 10 mission to Venus and Mercury, but the Voyager mission elevated it to an art form. Each encounter was carefully designed to place the spacecraft on a precise trajectory to the next planet. The most complex planning involved threading Voyager 2 through a series of 4 planetary encounters over a 12-year period. Achieving the necessary precision required innovations in spacecraft tracking and navigation. The position of each spacecraft was determined using a combination of radio, ranging, measuring the round-trip time of radio signals, and Doppler measurements, detecting the frequency shift in signals caused by the spacecraft's motion. These techniques could determine a spacecraft's position to within about 100 kilometers, 62 miles, even at Neptune's distance, equivalent to hitting a golf ball in New York and having it go into a specific hole on a golf course in Los Angeles. Course corrections were made using a hydrazine propulsion system with 16 small thrusters. These adjustments needed to be minimal. The spacecraft launched with only about 100 kilograms and 220 pounds of propellant, yet precise enough to achieve encounters within specific parameters to ensure both scientific return and proper trajectory for subsequent encounters. The propulsion system itself represented a significant engineering achievement. The thrusters needed to provide reliable, precisely controlled impulses, after years of inactivity in the cold of space. The system used pressure-fed hydrazine monopropellant with catalyst beds that could be heated electrically before firings, a design that has proven remarkably durable, with thrusters still functioning more than 45 years after launch. Scientific instruments, precision in harsh conditions. The Voyager spacecraft each carry 11 scientific instruments designed to study planetary atmospheres, magnetic fields, rings, satellites, and the interplanetary and interstellar medium. These instruments had to operate in environments ranging from the intense radiation near Jupiter to the near absolute zero of interstellar space. The imaging system consisted of 2 television-type cameras, a wide-angle camera and a narrow-angle camera for more detailed views. These used Vidicon tubes, a technology now obsolete on Earth, with selenium-sulfur photosensitive surfaces. The cameras could be fitted with various filters mounted on a wheel to observe in different wavelengths. Though primitive by modern standards, these cameras captured the iconic images that transformed our understanding of the outer solar system. Other optical instruments included an infrared interferometer spectrometer, an ultraviolet spectrometer, and a photopolarimeter. These instruments analyzed light in different wavelengths to determine the composition and structure of planetary atmospheres and surfaces. Each required precise optical alignment and calibration that had to be maintained despite the vibrations of launch and the thermal cycling of space. Particles and fields instruments included magnetometers, plasma detectors, cosmic ray telescopes, and plasma wave detectors. These were particularly valuable for studying planetary magnetospheres and, later, for detecting the boundary between the solar system and interstellar space. Many of these instruments were mounted on booms extending from the main spacecraft bus to isolate them from electromagnetic interference. The protection of sensitive electronics from radiation was a particular concern, especially for the Jupiter encounters where radiation levels were thousands of times higher than those that would be lethal to humans. Instruments and critical electronics were shielded using aluminum enclosures, and systems were designed with radiation-hardened components where possible. Software and operational innovations. Beyond the hardware challenges, the Voyager mission pioneered software and operational approaches that revolutionized deep space exploration. The concept of encounter sequences, detailed, pre-programmed sets of commands that would execute automatically during planetary flybys, allowed the spacecraft to conduct complex scientific observations without real-time control from Earth. These sequences were meticulously planned and tested, using computer simulations on Earth before being uploaded to the spacecraft. During the Neptune encounter in 1989, Voyager 2 to Earth only during scheduled communication sessions. Legacy of innovation. The technical innovations developed for the Voyager mission have influenced spacecraft design and operations for decades. The modular approach to spacecraft construction, redundant systems for critical functions, and the use of RTGs for deep space missions have become standard practices in planetary exploration. The gravity assist techniques pioneered by Voyager have enabled numerous subsequent missions, from Galileo's complex trajectory to Jupiter to Cassini's tour of the Saturn system and New Horizons' journey to Pluto. Without these techniques, much of our exploration of the outer solar system would have been impossible or prohibitively expensive. The communications technologies developed for receiving extremely faint signals have enhanced Earth's deep space listening capabilities, benefiting not only NASA missions, but also radio astronomy. Similarly, data compression techniques developed for transmitting Voyager images across limited bandwidth have influenced digital communications on Earth. Perhaps most importantly, the Voyager mission demonstrated the feasibility of designing spacecraft for extreme longevity. The engineering principles that have kept these spacecraft operating for more than 4 decades, robust design, redundant systems, maintainable software, and adaptable operations, have influenced the design of subsequent long-duration missions like Galileo, Cassini, and the Hubble Space Telescope. As humanity contemplates even more ambitious goals, from human missions to Mars to potential interstellar probes, the lessons learned from Voyager's remarkable journey continue to inform and inspire. The Voyagers stand as testament to human ingenuity, and the ability to create technology capable of operating in the most extreme environments imaginable, continuing to function and return valuable scientific data decades beyond their designed lifetime at the very edge of interstellar space. Legacy and future prospects. The Voyager mission stands as sessions. Heliosphere. One of the most significant recent discoveries came in 2012 to 2013, when Voyager 1 provided the first direct measurements of the interstellar plasma density, finding it approximately 40 times greater than the plasma inside the heliosphere. This measurement confirmed theoretical predictions about the nature of the interstellar medium and provided ground truth for models of the local galactic environment. In 2018, Voyager 2's crossing of the Heliopause provided a valuable second data point, revealing that the boundary appears to be somewhat permeable, allowing some particles to pass in both directions. This suggests that the interaction between the solar bubble and interstellar space is more complex than initially thought, with implications for understanding how stars interact with their galactic environments. Perhaps most intriguingly, in 2021, Voyager 1 detected a persistent hum in the interstellar plasma, a continuous low-level plasma wave signal that suggests the interstellar medium may be more dynamic than previously believed. This unexpected finding demonstrates that even after decades, the Voyagers can still deliver surprising discoveries that challenge our understanding of the cosmos. As the spacecraft continue their outward journey, they will soon encounter the hydrogen wall, a region where interstellar hydrogen piles up against the heliopause. Beyond this lies pristine interstellar space, unaffected by our sun's influence. Each additional year of operation allows the Voyagers to sample more distant regions of the interstellar medium, potentially revealing variations in its properties that could provide insights into the structure of our galactic neighborhood. Expected operational timeline. The finite power supply of the Voyager spacecraft imposes ultimate limits on their operational lifespan. Each spacecraft is powered by 3 radioisotope thermoelectric generators, RTGs, that convert heat from the radioactive decay of plutonium-238 into electricity. This power output diminishes over time, with a half-life of 87.7 years, requiring increasingly careful power management. At launch. In 1977, each spacecraft generated approximately 470 watts of electrical power. By 2023, this had declined to below 250 watts, less than required to operate all original systems simultaneously. Mission engineers have implemented a series of power-saving measures, systematically shutting down non-essential systems and instruments to extend the mission's duration. Heaters for certain instruments have been turned off, requiring these components to operate at temperatures below their design specifications. Some redundant systems have been powered down, accepting the increased risk in exchange for power conservation. Data transmission rates have been reduced to minimize the power required for communications. Current projections suggest that the RTGs will provide sufficient power to maintain minimal scientific operations until approximately 2025 to 2030. After this point, instruments will be sequentially powered down as available electricity diminishes. The spacecraft will likely maintain some level of communication capability for several years beyond the end of scientific operations, potentially allowing for basic engineering data to be returned even after science instruments are deactivated. The final communication with either Voyager spacecraft will represent a poignant milestone, the end of humanity's longest conversation across space. Yet, even after they fall silent, the Voyagers will continue their journey through the Milky Way galaxy, potentially lasting billions of years as silent ambassadors of human civilization. Trajectory and ultimate fate. The Voyager spacecraft are traveling along different trajectories out of the solar system, each headed toward different regions of the Milky Way galaxy. Voyager 1 is moving northward relative to the plane of the planets at a speed of about 38,000 miles per hour, 17 kilometers per second, while Voyager 2 is traveling southward at approximately 35,000 miles per hour, 15.8 kilometers per second. At these velocities, the Voyagers will require tens of thousands of years to reach the distance of the nearest stars. Voyager 1 is headed in the general direction of the constellation Ophiuchus, while Voyager 2 moves towards Sagittarius. Neither spacecraft will pass particularly close to any known star in the foreseeable future. Calculations suggest that Voyager 1 will pass within 1.6 light-years of the star, Gliese 445, in approximately 40,000 years, while Voyager 2 will pass about 1.7 light-years from the star Ross, 248, in about 40,000 years. Over much longer timescales, millions to billions of years, the spacecraft will participate in the orbital dance of stars around the galactic center, becoming truly interstellar wanderers. Barring an extremely unlikely collision with interstellar matter or capture by another star system, the Voyagers could potentially outlast Earth itself, continuing their silent journey through the galaxy long after our planet has been rendered uninhabitable by the sun's evolution into a red giant star billions of years from now. Or, this extraordinarily long potential lifespan gives special significance to the golden records carried by both spacecraft. These artifacts may become the longest-lasting evidence of human civilization, potentially discoverable by other intelligences long after humanity itself has vanished or evolved into forms unrecognizable to modern humans. Comparison to newer interstellar missions. The Voyagers were never specifically designed as interstellar probes. Their primary mission was planetary exploration, with their current interstellar journey representing an extended bonus phase. Several subsequent spacecraft have followed the Voyagers into the outer solar system, though none have yet crossed into interstellar space. The Pioneer 10 and 11 spacecraft, launched before the Voyagers in 1972 and 1973 respectively, also followed trajectories out of the solar system. However, both ceased communications years ago. Pioneer 10's last signal was received in 2003, and Pioneer 11's in 1995. Though both continue their silent journeys into interstellar space, they are not expected to cross the Heliopause for many years. New Horizons, which performed the first close flyby of Pluto in 2015 and visited the Kuiper Belt object Arrokoth in 2019, is following a path out of the solar system at a speed of about 33,000 miles per hour, 14.9 kilometers per second. However, it will require decades to reach the Heliopause. Currently operating in an extended mission phase exploring the outer solar system, New Horizons is expected to maintain power until the mid-2030s. Though it may not survive long enough to cross into interstellar space, several proposed mission concepts specifically targeting interstellar exploration have emerged in recent years. The most developed of these is NASA's Interstellar Probe, a concept study for a dedicated mission to explore the Heliosphere boundary and venture into nearby interstellar space. Unlike the Voyagers, which reached interstellar space after decades of extended operations, the Interstellar Probe would be designed specifically for this purpose, carrying modern instruments tailored to study the interstellar medium. Other more ambitious concepts include Breakthrough Starshot, a private initiative proposing to use powerful ground-based lasers to accelerate tiny star-chip spacecraft to 20% the speed of light, potentially reaching nearby star systems within decades rather than millennia. While technologically challenging, such concepts represent the next generation of interstellar exploration, building upon the foundation established by the Voyagers. Despite these newer initiatives, the Voyagers remain unique in having actually crossed the boundary into interstellar space. Their measurements provide ground truth against which theoretical models can be tested and future mission concepts evaluated, establishing an empirical baseline for humanity's understanding of the interstellar environment. Scientific legacy. Transforming planetary science. The scientific legacy of the Voyager mission extends far beyond its current interstellar phase. The planetary encounters fundamentally transformed our understanding of the outer solar system, replacing blurry telescopic views with detailed portraits of complex, dynamic worlds. At Jupiter, the Voyagers revealed the intricate dynamics of the Great Red Spot, discovered the volcanic activity on Io, identified the possibility of a subsurface ocean on Europa, and mapped the complex magnetosphere. At Saturn, they unveiled the intricate structure of the ring system, discovered shepherd moons, and provided the first detailed observations of Titan's atmosphere. Voyager 2's encounters with Uranus and Neptune revealed these ice giants to be distinct worlds with dynamic atmospheres, complex magnetic fields, and diverse moon systems rather than the featureless blue spheres they appeared from Earth. These discoveries transformed planetary science from a largely observational discipline into one that could study detailed processes such as comparative meteorology, magnetospheric physics, and satellite geology across multiple planetary systems. This comparative approach revealed both common physical principles operating throughout the solar system and the unique evolutionary paths that have created such diverse worlds. The Voyager discoveries continue to drive exploration priorities today. The evidence for a subsurface ocean on Europa directly influenced NASA's Europa Clipper mission, scheduled to launch in 2024. Similarly, the Voyager's tantalizing glimpses of Titan led to the Cassini-Huygens mission and the upcoming Dragonfly mission to this intriguing moon. Uranus and Neptune, visited only briefly by Voyager 2, are now considered high-priority targets for dedicated orbiter missions in the coming decades. Beyond specific discoveries, the Voyagers established a methodology for comprehensive planetary system exploration that has influenced subsequent missions from Galileo to Cassini to Juno. This approach treats each planetary system as an integrated whole, studying not just the planet itself, but its rings, moons, magnetosphere, and surrounding space environment to develop a complete understanding of its formation, evolution, and current state. Technological legacy influencing spacecraft design. The engineering achievements of the Voyager spacecraft have influenced the design of virtually every subsequent deep space mission. Their remarkable longevity demonstrated the value of robust design principles, redundant systems, and adaptable operations, lessons that have been applied to spacecraft from the Hubble Space Telescope to the Mars rovers. The Voyagers pioneered techniques for autonomous spacecraft operation, a necessity when communication delays stretch to hours or days. Their ability to execute complex observation sequences without real-time control, detect and respond to anomalies, and manage resources independently provided a model for increasingly autonomous spacecraft operations. The gravity assist trajectory techniques refined by Voyager mission planners have become standard tools for interplanetary mission design. These techniques have enabled missions that would otherwise be impossible or prohibitively expensive, from Cassini's tour of the Saturn system to Lucy's ongoing journey to multiple Jupiter-Trojan asteroids. Communications technologies developed to receive the Voyager's faint signals have enhanced deep space communications capabilities, benefiting both NASA missions and radio astronomy. Similarly, techniques for operating spacecraft with limited power and bandwidth have influenced the design of missions. Similarly, techniques for operating spacecraft with limited power and bandwidth have influenced the design of missions operating in challenging environments throughout the solar system. Perhaps most importantly, the Voyagers demonstrated the value of designing spacecraft for adaptability and longevity. The ability to reprogram the spacecraft to address new scientific questions or overcome hardware limitations has allowed the mission to evolve far beyond its original scope, establishing a precedent for extended missions that extract maximum scientific return from spacecraft investments. Cultural impact. Expanding human perspective. Beyond their scientific and technical accomplishments, the Voyager spacecraft have had a profound cultural impact, influencing how humanity views its place in the cosmos. The famous pale blue dot image, taken by Voyager 1 in 1990 at the request of astronomer Carl Sagan, shows Earth as a barely visible point of light from a distance of 3.7 billion miles. This image, accompanied by Sagan's eloquent reflection on its significance, has become an iconic symbol of Earth's fragility and the perspective that space exploration can provide. The Voyager's golden records represent a unique cultural artifact, time capsules intended to convey the diversity and richness of human experience to any extraterrestrial intelligence that might someday recover them. The process of selecting the contents, 115 images, greetings in 55 languages, natural sounds of Earth, and musical selections from different cultures, required humanity to consider how to represent itself to the cosmos, a profound exercise in collective self-reflection. In popular culture, the Voyagers have appeared in numerous films, television programs, and literary works, often symbolizing humanity's reach beyond Earth and the blend of technology and aspiration that characterizes space exploration. This cultural presence has helped maintain public awareness of and support for space exploration, even as the mission has continued for decades beyond its planned duration. The Voyagers have also influenced how we conceptualize the boundaries of our solar system. Prior to their crossing of the Heliopause, the edge of the solar system was an abstract concept. The Voyagers gave this boundary a concrete reality, providing empirical measurements of the transition between solar and galactic influence and expanding humanity's conception of its cosmic neighborhood. The future of interstellar exploration. As the Voyagers approach the end of their operational lives, they pave the way for the next generation of interstellar exploration. Their measurements of the interstellar medium provide essential data for designing future missions, while their journey has demonstrated both the possibilities and limitations of current propulsion and power generation technologies. The proposed interstellar probe mission would build directly on the Voyager's legacy, carrying modern instruments specifically designed to study the Heliosphere boundary and nearby interstellar space. With a planned launch in the 2030s and an operational lifetime of 50-plus years, this mission would provide continuity in humanity's exploration of interstellar space. More ambitious concepts like Breakthrough Starshot aim to overcome the speed limitations that constrain conventional spacecraft like the Voyagers. By developing technologies to accelerate small probes to significant fractions of the speed of light, such initiatives hope to enable exploration of nearby star systems within a human lifetime, rather than the tens of thousands of years required at Voyager-like velocities. The technical challenges of true interstellar exploration remain formidable, generating sufficient power for decades of operation far from the Sun, maintaining communication across interstellar distances, achieving the velocities necessary to reach other stars within reasonable timeframes, and designing spacecraft to operate autonomously for years or decades all require significant advances beyond current capabilities. Yet the Voyagers have demonstrated that apparently insurmountable challenges can be overcome through innovation, persistence, and careful engineering. Their journey from Earth to interstellar space, accomplished with 1970s technology and lasting decades beyond their designed lifetime, offers inspiration for even more ambitious future exploration. As humanity contemplates its long-term future in space, the Voyagers remind us that our reach can exceed our immediate grasp. Their continuing journey into the Milky Way represents humanity's first tentative physical venture beyond our solar system, not merely observing the stars from afar, but sending our creations among them. Whatever form future interstellar exploration takes, it will build upon the foundation established by these pioneering spacecraft made at the edge of the solar system, but destined for the stars. As the Voyager spacecraft continue their silent journey into the cosmos, they carry with them more than scientific instruments and golden records. They bear the legacy of human ingenuity, curiosity, and hope, tangible evidence of a civilization that dared to reach beyond its planetary cradle. Though their power will eventually fade and their signals grow too faint to detect, the Voyagers will endure as humanity's first interstellar ambassadors, potentially outlasting Earth itself as they drift among the stars for billions of years. The remarkable journey of these twin spacecraft has transformed our understanding of the solar system, challenged our conception of cosmic boundaries, and expanded our technological capabilities. From the volcanic landscapes of Io to the azure mysteries of Neptune, from the radiation belts of Jupiter to the hydrogen wall at the edge of interstellar space, the Voyagers have revealed the diversity and complexity of our cosmic neighborhood, while demonstrating the extraordinary possibilities that emerge when human creativity confronts the unknown. Perhaps most profoundly, the Voyagers have altered our perspective on Earth itself, a pale blue dot in the vastness of space, yet the only known harbor of life in the cosmic ocean. As they recede ever further into the blackness between the stars, they remind us of both our cosmic insignificance and our remarkable capacity to comprehend the universe that contains us. In this way, the Voyagers embody the essence of exploration, not merely to discover what lies beyond the horizon, but to better understand our place within the grand cosmic tapestry.